Hello students, welcome to the class. Today we are going to start with our next topic, that is physical world units and measurement. Okay, so this physical world units and measurement, actually if you see the textbook, it is a first topic we see that as a physical world in our PUC first year, and second topic it is units and measurements and dimensions, right? Okay, so while discussing in this neat question pattern, we take these two chapters together and we discuss here, right? So let us discuss these two chapters together. First all the synopsis, then we can go for the synopsis part. Okay, so physical world units and measurement and dimensions. In this chapter, in physical world, we will mainly come across hardly one question may come from this part. Okay, only one question will be there. Then physical world, it consists of contains like different forces. We will come to the picture, that is fundamental forces, right? What do you mean by physical quantity, types of physical quantity? Then next prefixes, what are the fundamental and derived quantities? So all together we will discuss in this chapter, right? So this is the very basic chapter. These two are very basic concept here, right? So let us see the first slide, that is physical world. See here, that is in physical world, first we see there are four fundamental forces in nature. Okay, we will see that there are four fundamental forces in nature. So how many fundamental forces are there? We have fundamental forces. In these fundamental forces, there are total four fundamental forces in nature. So which are those? Here we have the first fundamental force as gravitational force. Then next we have electromagnetic force. Third one we have strong nuclear force. And fourth one is weak nuclear force. These are the four fundamental forces in nature. So before this also we see some concepts like how science and technology is related. So if you see the theory part, that all concept we discuss, how science and technology is related and what do you mean by physics, that all concepts we study in physical world chapter. But here we are discussing only the main point, that is fundamental forces. Okay, so what is the importance of this chapter, that is physical world? It tells you about the importance of physics. It tells you about the importance of physics here. Physics laws, right? So what do you mean by physics? That we learn from this chapter only. Physics is nothing but what? It is the study of nature and natural phenomena. The study of nature and natural phenomena is called as what? Physics here. Okay, so in physics, whatever the laws we will discuss, all the laws directly, we don't give the conclusion for the laws. Here to study the laws, we will follow certain steps. We will follow certain steps here, right? So first we will observe the phenomena, then what we will do, then here we will make a model of those phenomena, then we will study that in different conditions. So like that we do the study, then we give conclusion of laws here. Okay, so then next, science and technology and society, how these three are related here. Whatever the contribution of technology is there, that is based on physics here. If you take any technology nowadays, what you are using, like mobiles, laptops, whatever you are using, so these all principles and the functions are explained based on physics and physical laws here, right? Therefore physics and technology is related. So whatever technology is there, it is very useful for the society. So like this we say that physics, technology and society are interrelated with each other, right? Then here let us start with the main point, that is fundamental forces. In fundamental forces, the first force is called as gravitational force. So what do you mean by gravitational force? See here, gravitational force, it is due to mass of the two bodies. So what do you mean by gravitational force here? Gravitational force is nothing but it is because of the mass of the two bodies. Suppose if if we have two bodies here, you can name A body and B body irrespective of the masses. Okay, means irrespective of the masses, in the sense it is not necessary that both should be of the same size. One is of bigger size, one is of smaller size. It is not at all like that. Suppose if you assume the masses are M1 and M2. Suppose if you assume the masses are M2, M1 and M2, the center between the masses, if the center between the masses, if it is the distances r, then here m1 exerts force on m2 and m2 exerts force on m1. Therefore we take it as the force between them, it is due to the whatever the force is exerting by A on B and B on A, it is due to the masses. It is because of the mass of the two bodies. Here, whatever the gravitational forces there, it is always attractive in nature. The forces are always attractive in nature, which means that whenever any two objects are placed, they will be always attracting each other. It is never a repulsive force. Sometimes if it is not attracting also, it is not a repulsive force also. Okay, we never say that the gravitational force is a repulsive force. It is always a attractive force here. Gravitational force is attractive force. Means one body exerts force on the other body. So like this, the force of attraction will be there between the two bodies. Is it clear? This is what? This is related to gravitational force. The forces are due to the mass of the two bodies and it is always attractive in nature. The force is always attractive in nature. Third point, it operates in all objects of universe. It operates in the all objects, which means that whatever the gravitational force is there, this force is always applied for all the bodies in the universe. It is applied for all the bodies in the universe, we say that. Okay. The next point, its range is infinite, which means that here whatever the gravitational force range is there, it is infinite. So last point and the very important point is, compared to all four fundamental forces in nature, this gravitational force is the weakest force. We say that compared to all the four fundamental forces in nature, gravitational force the weakest force in the nature compared to all these four. And here see 10 to the power of minus 38 times compared to strong nuclear forces. So what is the meaning of this? Here the gravitational force is 10 raised to minus 38 times smaller than the strong nuclear force. So this is for gravitational force. The next force we have, that is electromagnetic force. So what do you mean by electromagnetic force here? Electromagnetic force, when it exists and how it exists, let us see. This electromagnetic force, it is due to the stationary or a moving electrical charge. The force is due to the stationary or moving electrical charges. Okay, so that is called as what? Electromagnetic force. Means suppose if you take two charges here, if I have one is plus charge and other one is also plus charge, here whatever the force between these two charges are there, this is what, either it may be rest or if it is in a moving, the force between them we take it as what? Electromagnetic force. Or here what happens, they will repel each other. That is, force of repulsion will be there. Suppose if you take one is positive, one is negative, here what happens? The force of attraction will be there. Force of attraction will be there. So it is due to stationary or a moving electrical charge. Next point, it may be attractive or repulsive. Here, as I said, if it is same charge, they will repel each other. If it is opposite or the unlike charges, they will attract each other. It operates on charged particle. Here this force operates on a charged particles, means both the bodies should be charged here. Then only the electromagnetic force come to an existence. And the range is, it is also a finite range, infinite range. Then it is 10 to the power of 36 times stronger than the gravitational force, but 10 raised to minus 2 times smaller than the strong nuclear force. Okay. That is regarding the electromagnetic force. Then next. Strong nuclear force. So here students, what do you mean by strong nuclear force? Strong nuclear force is nothing but it operates between the nucleons. So here the question comes, what do you mean by nucleons? Nucleons are nothing but, see here, that is, suppose if you consider any one radioactive element, I'll consider uranium. So uranium 92-238, when it is bombarded with neutron, it will give. So it will give, that is its daughter nuclei like krypton, beryllium and all. So this is what, this is radioactive phenomena. Here what they have given, with strong nuclear forces between the nucleons in the sense that is, suppose if you take an atom, so in the atom we will be having a nucleus. In this nucleus we have neutrons and protons, and the electrons are revolving in the orbit. So neutrons and protons together, it is called as what? Nucleons. Neutrons and protons together, it is called as nucleons. So here the force between these nucleons, it is called as what? Strong nuclear force. It is strong nuclear force. And here they are saying that it is maybe attractive or it may be repulsive in nature, which means that, see here, as I said, the gravitational force, it is always attractive in nature, it is never repulsive force. Then next we have electromagnetic force. So this electromagnetic force, it is always, it is also attractive or repulsive. In the same way, this strong nuclear force is what? It may be attractive or repulsive. Its range is very short within nuclear size. Its range is what? Very short within nuclear size, which means that here whatever the range of the force is there, it is very short because it acts within the nucleus only. But gravitational force, it acts for the large distance. Electromagnetic force also same, but here the strong nuclear force, it acts within the nucleus, therefore it is very short range. It is very short range force, but it is the strongest force in the nature. Okay, so this is regarding what? Strong nuclear force. So remember, strong nuclear force acts between the nucleons. That is, whatever the protons, neutrons are there, it acts within that. Right. Next, weak nuclear force. Weak nuclear force is what? Here it operates within the nucleons. That is, elementary particles like electron and neutrino. Okay. Weak nuclear force is what? It acts within the nucleons. That is, elementary particles like electron and neutrino, they are saying. It appears during the radioactive beta decay. So just now I was explaining regarding the radioactivity phenomena. Radioactivity is what? That is uranium neutron. When uranium is bombarded with neutron, it will give the daughter nuclei. So during that time, different decay we study, like alpha decay, beta decay and gamma decay. So during the beta decay, whatever the elementary particles are released. Between them, the force is called as what? Weak nuclear force. It has very short range, that is 10 raised to minus 15 meter and 10 to the power of minus 13 times than strong nuclear force. So this is regarding your, what you can say, all the four fundamental forces in nature. Okay. Then next, we have, after discussing about the four fundamental forces in nature, next we are going to discuss physical quantity. Let us see what do you mean by physical quantity. Okay, so physical quantity means what? See, in physics, we use many terms like force, pressure, mass, length, time, temperature, electric current, electric potential, resistance. Then we have density, volume. So many terms we use in physics. So what are these quantities are called as? These quantities we term it as physical quantity. So what do you mean by physical quantity? A quantity which can be measured and by which various physical happenings can be explained and expressed in the form of laws is called a physical quantity. Means here it is nothing but it is a quantity. Okay, so this quantity, it can be explained and expressed in the form of laws, which can be expressed and explained in the form of laws is called as what? Physical quantity. So the example for a physical quantity is mass, length, time, temperature, force, pressure, density, volume, right? So like this, whatever terms we use in physics, all the terms are physical quantity. Why? Because you can express it as well as you can explain it, you can measure it. Therefore, it is called as what? Physical quantity. Then in physical quantity, we have different types. Then we have different terms which we use here. Okay, so first let us see the types of physical quantity. So out of large number of physical quantities which exist in the nature, there are only few quantities which are independent of all other quantities and do not require the help of any other physical quantity for their definition. So this is called as what? Fundamental quantities. What is the meaning of this? See here students, we have the physical quantity. There are two types of physical quantity. One is fundamental quantity and the other one is derived quantity. So what do you mean by fundamental quantity here? Fundamental quantity means these are the quantities which exist in the nature. There are only few quantities which are independent of all other quantities, which are independent of what? All other quantities, and they do not require the help of any other physical quantity for their definition. Means if you see the example, you will understand the definition clearly. Why? Because whatever the quantities we use in physics, here some quantities are not depending on others. For example, if I say length, so length, how you do the measurement? So length measurement is nothing but what? You can take a scale or a measuring devices, you can measure the length directly. So to measure the length, you don't require any other quantity again, right? So if you want to measure time, so you will see the time in the watch, then you will measure it. Again, you don't require any help of any quantity. So this is what? Fundamental. These two are just, I'm giving you example. These two are our fundamental quantity. Okay, what do you mean by derived quantity here? Derived quantity in the sense, you can see there are some quantities like, So if I say a quantity, that is force. So force, how you write force is equal to, it is mass into acceleration. Force is what? It is mass into acceleration. You can see here force is depending on mass, force is depending on mass and acceleration. You can see that the force is defined and measured with the help of these two quantities. In that, one is a fundamental quantity. Therefore, the quantities which are not depending on anything for the measurement, or you can say the quantities which are independent of all other quantities, are called fundamental quantities, and the quantities which are dependent on other quantities are called as derived quantity. I hope the fundamental and derived quantity definitions are clear to you. Okay. So you can see that next it is written. Therefore, these are called what? Absolute quantities. Fundamental quantities are also called as what? Absolute quantities. These quantities are also called fundamental or base quantities, as all other quantities are based upon and can be expressed in terms of these quantities. Then next, derived quantities. All other physical quantities can be derived by suitable multiplication or division of different powers of fundamental quantities. Okay, so all other fundamental physical quantities can be derived by suitable multiplication or division. Just now I showed you that is force is equal to mass into acceleration. The product of mass and acceleration, we take it as what? Derived quantity. Okay, so product is there. You can take one example of division also, that the division is nothing but acceleration is equal to rate of change of velocity. So this is what two physical quantities are in division. Okay, so such quantities are called as what? Derived quantity. Or in simple words, we can also say that the quantities which are depending on the fundamental quantities are called as derived quantity. So if length is defined as a fundamental quantity, then area and volume are derived from length and are expressed in terms of length with the power 2 and 3 over the term of length. Means the meaning of this statement is, that is, length can be written as, it is directly measurement, but volume, how you write? Length into breadth into height. Volume can be written as length into breadth into height. Therefore it can be written as what? L raised to 3 L cube. It can be written as L cube. Then volume can be written as, that is, volume is L cube. Area can be written as length into breadth, that is L square. So such type of quantities are called as what? Derived quantities. Okay, then next, fundamental and derived units. Any unit of mass, length and time in mechanics is called a fundamental or absolute base unit. Other units, means in simple words, we can say that the unit of a fundamental quantities are called as fundamental units, and the unit of a derived quantities are called as what? Derived unit. Okay, so fundamental unit example is mass ka kg, then time is second, length is meter. These are example for fundamental units. Derived unit examples are like meter per second square, kg, meter per second. So there are many fundamental and derived units, right? Then next, see here we have the different types of unit also again. See here, before going to see the next type of physical quantity, already just now we defined derived and fundamental physical quantities. Here again we have the type of physical quantity. Just now what we derived, fundamental and derived quantities, those are based on the formulas. Here, based on magnitude and direction, we have the types of physical quantities. So before going to these types, see here one definition we have, that is ratio, or it is a numerical value. Okay, when a physical quantity is a ratio of two similar quantities, it has no unit. Okay, so for example, if you say the relative density is the ratio of what? Density of object divided by density of water at 4 degrees Celsius. That is relative density. Similarly, refractive index, it is the ratio of velocity of light in air or vacuum to the velocity of light in medium. This is refractive index. Then strain, change in the dimension to the original dimension is called as what? Strain. Here what we want to say is, that is whatever the ratios are there, if it is of the same quantity, then it has no unit. It has no unit. That is called as numerical value only, and that only we say it as magnitude. So again, we have two types of physical quantities. In these two types of physical quantity, that is scalars and vectors. So what do you mean by scalar here? Scalar is nothing but the quantities which has only magnitude. The quantities which has only magnitude, no direction, is called as a scalar quantity. Example, length, time, work, energy, etc. are the example for scalar quantity, which has only magnitude, are called as scalar quantity. Okay, then next, vector quantity. So vector quantity is means what? The quantities which has both magnitude and direction is called as a vector quantity. So examples are displacement, velocity, acceleration, force, etc. So vector physical quantities can be added or subtracted according to vector laws of addition. These laws are different from the law of ordinary addition. See here students, I said that scalar quantity means what? Which has only magnitude. Examples are like length, time, work, energy, mass. These are all what? Scalar quantity. How we say that? See, while measuring the time, you just say whatever the respective time is there. You don't specify the direction. In the same way, when you are measuring the length, you just measure the length as 10 meter. You don't specify in which direction you are measuring. If you specify the direction, then it becomes vector quantity. Okay, so the quantities which has only magnitude are called as scalar quantity. The quantities which has both magnitude and direction are called as vector quantity. Is it clear? Okay. Next. So after scalar quantity and vector quantity, see here. There is one note, there are certain physical quantities which behave neither as a scalar or nor as a vector quantity. Like a moment of inertia is not a vector, as by changing the sense of rotation, its value is not changed. It is also not a scalar, as it has different directions or axis of rotation. Such physical quantities are called as what? Tensors. So we have some physical quantity which either behave as a scalar quantity or as a vector quantity. So such quantities we take it as a tensor quantity. So example they have given, that is moment of inertia. Moment of inertia is what? It is the example for tensor quantity, right? So if I say you are doing the measurement of length as 10 meter, this is what distance measurement, then it is scalar quantity. If I say that the distance covered is 10 meter towards east, then it is what? Displacement, then it is a vector quantity. So only the thing is what you need to remember, scalar and vector quantity. So the definition and the example, right? Next. The system of units. So what do you mean by unit here? See here students, whenever you are measuring any physical quantity, like just one small example, simple one, that is mass. Mass is what? It is a physical quantity. Mass is a physical quantity. How you measure the mass? Mass, I'll take it as 10 kg. So you will go to shop, you will get sugar of 10 kg. So here 10 is what? 10 is the numerical number. Kg is what? Kg is the unit. If you see any physical quantity, it has two parts. One is a numerical value, that is a number, and other one is a unit here. Numerical value and unit, right? So such physical quantity always consists of two parts. One is a numerical number and other one is a unit here. Okay. This unit, if you specify the unit, then it is understood that it is a mass measurement. Suppose if you go to shop, if you say only 10 of sugar, what is this 10 of sugar? So it is a 10 kg, 10 gram, 10 quintal, right? So you need to specify the unit that will give the proper meaning to your physical quantity. Okay, so it is not necessary that we need to have only a proper unit, proper number. The proper unit is also compulsory. If you go and say that is give 10 seconds of this one rice, then what is the meaning of the statement? It is a meaningless statement, right? So here the thing is what, when you specify any physical quantity along with its unit, then it will give the correct meaning. If I say it is 10 meter, it means that it is the measurement of what? Length. If I say it is 25 seconds, it is the measurement of what? Time. Means the unit specifies the physical quantity. Okay. So in the previous slide, we have discussed about the fundamental quantities. So the fundamental quantities, total we have 7 fundamental quantities, students. So which are the 7 fundamental quantities are there? Let us see. Fundamental quantities, there are total 7 fundamental quantities are there, like mass, length, time, temperature, electric current, amount of substance, and luminous intensity. So these are called as what? Fundamental quantities. These are called as fundamental quantities. Okay, so you can see all the 7 quantities are not depending on any other quantity. Therefore, it is called as what? Fundamental quantity. Therefore, it is called as fundamental quantity. Is it clear? Okay. Then the unit of such fundamental quantities are called as what? Fundamental unit. Then derived quantity. Derived quantity except these 7. Which are the 7? Mass, length, time, temperature, electric current, amount of substance, luminous intensity. These are what? These are fundamental, except that whatever the units you take, those are what? Derived units and the derived physical quantity. So here, see that there are 4 system of units, that is CGS system, MKS system, and FPS system, and SI system. There are total 4 system of units. Okay, so to define any physical quantity, we require a unit, the complete set of units which has both fundamental and derived for all kind of physical quantities is called what? System of units. The common systems are given below. So there are 4 system of units. So out of 4, we use only the last one for all the calculation, that is SI system. So let us just discuss what are the other 3 system here. The first one is CGS system. The system is also called Gaussian system of units. In its length, mass, and time have been chosen as the fundamental quantities, and corresponding fundamental units are centimeter, gram, seconds. So I'll just show you one table so that you can understand this clear way. That is, I'll take here 3 fundamental quantities. One is mass, length, time. Then we have 4 system of units. One is CGS, one is MKS, FPS, and SI. So in all the 4 fundamental quantities, the unit of mass for CGS, it is CGS. G stands for gram here. G stands for gram. Length is measured in terms of centimeter. Length is measured in terms of centimeter. Then next, MKS system. In MKS system, mass is measured in terms of kilogram. Mass is measured in terms of kilogram, and length is measured in terms of meter. And time in both the cases, it is second and seconds and seconds. That is the unit of time. Then FPS system. FPS system is what? Here the system where the unit of mass is pound, unit of length is foot, and unit of time is second. Then SI system. In SI system, we have the unit of mass as kg. It is length is meter, time is second. So these are what? These are the 4 system of units. So here in one table only you can show all the 4 instead of reading this paragraph. Just once we will see. That is the CGS is what the system is called Gaussian system of units. It is length, mass and time have been chosen as a fundamental quantities and corresponding fundamental units are centimeter, gram and second. MKS system is also called Georgi system. So this Georgi system, here the units are, that is meter, meter is for length, then kg is for mass, then second is for time. FPS system. FPS system, the length is measured in terms of foot, then pound, then second. Then SI system, it is also known as International System of Units or System International. Here it is an extended system of unit applied to the whole physics. These are 7 fundamental quantities in the system. These quantities and their units are given in the following table. So let us see the next slide. See here, that is mass, length and time. Okay, these are the fundamental quantities here. You can see the table. Quantities are like length, mass, time, electric current, temperature, amount of substance and luminous intensity. Okay. So here the unit of length is, the unit of length is taken as meter and the symbol is denoted by m, and mass, the unit of mass is kilogram and it is denoted by kg. The unit of time is second and it is denoted by S. The unit of temperature is Kelvin and it is denoted by K. The amount of substance is taken as mole. Amount of substance is taken as mole, written as MOL. And luminous intensity is written as candela CD. Besides the above 7 fundamental units, 2 supplementary units are also defined, that is radian for plane angle and steradian for solid angle. So these are the 2 units which are taken for supplementary units. So these 7 we take it as a fundamental unit. Except these 7, we have 2 more supplementary units. Those are steradian and radian. Radian is denoted by RAD, symbol is, steradian is SR. Steradian is therefore solid angle that comes in the 3-dimensional. Then plane angle, it is a 2-dimensional angle, right? So these are the regarding units of fundamental quantities. Then next, except this, whatever it is there, that all we take under what this one derived units. So how we write the unit of such quantities? I'll just tell you how to write the unit here. See, that is, so suppose if you take force is a fundamental, this derived quantity. The formula for force is mass into acceleration. So mass is measured in terms of kg, acceleration is taken in terms of meter per second square. So kg meter per second square is the unit of force here, and this kg meter per second square, we take it as Newton. We take it as Newton. Similarly, we can write it for velocity. Velocity is what? It is displacement divided by time. It is displacement divided by time here, that is equal to. So that is equal to, displacement is written as meter and time is taken as second. Therefore, it is meter per second. It is meter per second. Okay, this is how we write the derived units. We can take one more. Any difficult quantities, we can write the units by ourselves without remembering much about this. Momentum is equal to mass into velocity. Mass is taken as kg. Then velocity is taken as meter per second. Okay, so we can take another unit, that is, I'll take it as density. So density, if I take density is equal to, what is the formula? It is mass per unit volume. Mass is taken as kg, volume should be taken as meter cube. Therefore, it is kg per meter cube. It is kg per meter cube is the unit of density. Is it clear? So similarly, we can write other units also. If I take impulse, so impulse is also a derived quantity. The unit of impulse, it is force into time. So force is taken as Newton, time is taken as second. So this is the unit of impulse. Then next, I'll take torque, T-O-R-Q-U-E. So torque is what? Force into perpendicular distance. Force is again Newton and perpendicular distance is meter. So Newton meter is the unit of torque here. Similarly, I can take pressure also. So if I take here pressure, pressure is equal to force per unit area. Force is taken as Newton and area is taken as meter square. That is nothing but Newton per meter square. This Newton per meter square, we take it as what? Pascal. We take it as Pascal. This is the unit of pressure. Like this, we can write unit of any other physical quantity. Only the thing is, we should know the formulas here. By knowing the formulas, we can convert, we can write the dimensional, the unit of any physical quantity. Is it clear, students? So symbol and the units. See here, one more point you need to remember. Whenever you are writing the unit, which is the name of a scientist, it should be written with the capital letter. It should be written with a capital letter. Suppose if you are writing any unit whose name, if it is not a scientist name, then you can write it in a small letter. This is the rule what you need to follow, right? Okay, so this is regarding the derived units. So then next, let us see the dimensions, dimension formula and all. See the next concept, that dimensions of a physical quantity. So when a derived quantity is expressed in terms of fundamental quantities, okay, means here any quantity it may be, either if it is means except fundamental. Okay, here the derived quantities, suppose if you take force, for whatever the force you are taking, the force should be expressed in terms of fundamental quantity. It should be expressed in terms of what? Fundamental quantity, right? Here fundamental quantities, that too we take the basic fundamental quantities like mass, length and time, m, l, t we take. It is written as a product of different powers of fundamental quantities, and the powers to which fundamental quantities must be raised in order to express the given physical quantities are called what? Dimension. So dimension is nothing but what? Expressing a given physical quantity in terms of fundamental quantity. In terms of fundamental quantity, we express it, and then after expressing, we write it in terms of what? We write it in terms of raise the power to the fundamental quantities. Means, for example, so if I take here force, or we can take pressure also. So first we will see the basic one, force. Force is equal to, we write mass into acceleration. So mass is a fundamental quantity, but acceleration is not a fundamental quantity. So how to write the dimension of this force? We need to express it in terms of mLT. So this m I can write as it is. So always it should be written in a square bracket. So first and capital letter mLT. So first mass I'll write as it is. This acceleration. Acceleration can be written as what? Change in velocity divided by time. Now you can see the time is a fundamental quantity, but velocity is not a fundamental quantity. Therefore, again, what we need to do is mass I'll keep as it is. Velocity can be written as what? Displacement. Velocity can be written as displacement by time. Already time is there, therefore it becomes t square. Therefore, here we can write it as m. Displacement we write it as L. Time we take it as t raised to minus 2. So m L t raised to minus 2 is the unit of what? Force. Dimensional formula for force here. We can take any physical quantity and we can express the dimensions in terms of m, L and t. I'll take pressure. So pressure is equal to what? Force per unit area is equal to, force is what? M, L, t raised to minus 2 divided by area is written as what? Length into breadth, that is L into L. Simplify now. M to the power, it is 1 only. L to the power, denominator 2 is there, numerator 1 is there. So 1 minus 2, it is minus 1, t raised to minus 2. That is m raised to 1, L raised to minus 1, t raised to minus 2 is the dimensional formula for pressure. It is the dimensional formula for pressure here. Is it clear? So this is how we write the dimensional formula for given different quantities. So any quantities you can take, we need to express those quantities in terms of m, L and t. Then next we need to raise the power here. Getting? And always this should be written with the capital letter and this should be expressed in a square bracket. So in the next slide we have different quantities. Let us see that. So how we will get the this one, dimensional formula and the unit of those quantities. It is basically, it is applicable for derived quantities especially. Okay. Here. So in physics we take many dimensional formula. You can see the first one is velocity or speed. So velocity or speed, the unit is taken as meter per second. How we write it is as meter per second. It is velocity or speed is nothing but what? It is distance or displacement. So here I'll just write here side so that you can understand it. So the first one we have it for velocity. So velocity is equal to, it is distance divided by time. So distance is expressed in terms of meter and time is in terms of second, therefore it is meter per second. Velocity and speed we take it as same. Then dimensional formula for distance, this is taken as L and for time it is taken as t. Therefore the unit becomes, the dimensional formula becomes m raised to 0, L raised to 1, t raised to minus 1. That is for velocity or speed. Then next we have acceleration. So for acceleration it is meter per second square. For acceleration it is meter per second square. That is m raised to 0, L raised to 1, t raised to minus 2. Why? Because here what happens for acceleration? That is, for acceleration we write acceleration is equal to velocity by time, that is equal to velocity is displacement by time. So time into time it becomes what? Time square, that is equal to, so m displacement is L, t raised to minus 2. That is m raised to 0, L raised to 1, t raised to minus 2 is for what? Acceleration. And unit is, velocity is written as meter per second and time is written as second. Therefore, it is meter per second square. Then next, acceleration is completed. Momentum. Momentum just now I written. Momentum is equal to what? Mass into velocity. So mass is kg, velocity is meter per second. That is nothing but, so well, mass is taken as m, velocity is taken as L t raised to minus 1. Therefore, it is m raised to 1, L raised to 1, t raised to minus 1. That is for momentum. Impulse also just now I said. So impulse can be written as, it can be written as the product of force and time. Product of force and time is impulse. So the dimensional formula is m raised to 1, L raised to 1, t raised to minus 1, and the unit is Newton second. Newton second. Then next, force. Many times we have seen in the previous slide. So force can be written as mass into acceleration, that is kg meter per second square, or it can be also written as Newton. And here the dimensional formula is m raised to 1, L raised to 1, t raised to minus 2. Then next, similarly, for pressure. So pressure, what is the formula for pressure here? Pressure is nothing but what? Force per unit area. One second, here we can erase this and we can see. That is pressure. So here the pressure can be written as, pressure is equal to force per unit area. So for force we take it in terms of Newton, and area we take it in terms of meter square. This is Newton per meter square. So this Newton per meter square we take it as Pascal, and the dimensional formula we write it in terms of, that is for force, here it is m L t raised to minus 2. It is m L t raised to minus 2 is for force, and for area it is L raised to 2. If it comes to the numerator, it becomes L raised to minus 2. Now if I simplify, I'll get it as m raised to 1, L raised to minus 1, t raised to minus 2. This is for pressure. Okay. Then next, for kinetic energy. So for kinetic energy, how we write? So for kinetic energy, we take it as, kinetic energy, we take it as half mv square. Kinetic energy, we take it as half mv square. So 1 by 2 m into v square. So numbers are not having any dimensional formula. So leave that, half mv square. So m how we write? So for mass, I'll take it as m itself. Velocity. So velocity, I can take it as L t raised to minus 1 to the power of 2. Therefore, we can simplify and write it as m L raised to 2 t raised to minus 2. You can see the kinetic energy. If you want to write it for potential energy, if you want to write it for potential energy. So potential energy, what is the formula? It is mgh. Okay, so m, I'll write as it is. G, acceleration. Just now we have simplified for acceleration. This is L t raised to minus 2, and again length is L itself. Therefore, if I write it, it becomes, it can be written as m raised to 1, L raised to 2, t raised to minus 2. Can you see here the potential energy and the kinetic energy both are having the same dimensional formula? Yes. So here, what we can say from this is, how many types of physical quantities are there? Compared to the dimensional formula, the number of physical quantities are more. Why? Because there are some physical quantities which are having the same dimensional formula. Is it clear? That is, potential energy is mg h, m raised to 1, L raised to 2, t raised to minus 2. Right? So this is regarding the potential energy and kinetic energy dimensional formula, and unit we already know. The kinetic energy or potential energy, it is measured in terms of what? Joules. Then next, power. So for power, how to write it? See. So for power, power is written as we write power is equal to work done per unit time. So for work done, before seeing the power, we need to see the work done formula. So work done is equal to what? This force into displacement. So force is written as ml t raised to minus 2. You can see from the above table. Then into displacement is L again. Therefore, this can be written as m L raised to 2 t raised to minus 2. This is for work done. That is m L raised to 2 t raised to minus 2 for work done. We want power here. Therefore, this can be written as m L raised to 2 t raised to minus 2 whole divided by t. So if I simplify this, I'll get it as m L raised to 2 t raised to minus 3. This is the dimensional formula for power here, right? Then next we have density. Density can be written as kg per meter cube. That is m raised to 1, L raised to minus 3, t raised to 0. So how density can be written? That is, here density is nothing but it is mass per unit volume. So mass is taken as kg, volume is taken as length into breadth into height, that is meter cube. This is nothing but kg per meter cube. This is nothing but kg per meter cube is for what? Density. Now we will write the dimensional formula here. Mass it is m, volume it is L raised to 3, but it is in the denominator, so therefore it becomes L raised to minus 3. So this is nothing but m raised to 1, L raised to minus 3, t raised to 0. This is for density. Then next we have angular displacement, that is theta is equal to. So angular displacement is what? It is nothing but the measurement of angle. Okay. So in a circular motion, we consider this angular displacement. Here what happens? It is m raised to 0, L raised to 0, t raised to 0. Why? Because here it is in terms of angle, right? Therefore, we take the dimensional formula for angular displacement as m raised to 0, L raised to 0, and t raised to 0. Next, angular velocity. So angular velocity is written as the unit is radian per second, and the dimensional formula is L raised to m raised to 0, L raised to 0, t raised to minus 1. Why? Because angular velocity is defined as angular displacement divided by time. Therefore, it becomes m raised to 0, L raised to 0, t raised to minus 1. Then next we have angular acceleration, that is alpha. It can be written as, so m raised to 0, L raised to 0, t raised to minus 2. Why? Because it is the ratio of angular velocity to time. That is m raised to 0, L raised to 0, and t raised to minus 2. Then next we have moment of inertia. Moment of inertia is nothing but the unit of moment of inertia is, here it is, this moment of inertia can be written as moment of inertia is equal to. So moment of inertia is equal to, the formula is mass into the square of perpendicular distances. Therefore, here mass is m and the distance becomes L square t raised to 0. Therefore, the unit is kg meter square. The unit is kg meter square. So after moment of inertia, here we have the last one, that is torque. So like this we can write for many physical quantities. Then next we have for torque here. Torque can be written as, torque is nothing but it is force into perpendicular distance. So force is Newton and perpendicular distance is meter. Newton meter is the unit, and the dimensional formula is written as ml t raised to minus 2 into L. That is nothing but ml raised to 2 t raised to minus 2. So in the square bracket we need to write it. So like this we write the dimensional formula for different physical quantity. First, the foremost thing is you need to know the formula. Then only you can write the dimensional formula, and you can write the what you can say, and you can write this the dimensional formula as well as unit by knowing the formula of a given physical quantity. Here one more point, students, that is here we define the law of homogeneity, or we call it as principle of homogeneity. So what is the principle of homogeneity here? The principle of homogeneity is the dimension of LHS must be equal to the dimension of RH. Yes, in the next class, in the next slides, we will be seeing this. Here I am just saying you, that is what is equation of homogeneity. Equation of homogeneity is nothing but the right hand side dimensions must be equal to the left hand side dimensions. So how we write that is, for example, so simple one we will take, force is equal to mass into acceleration. We know that force is, now we should know both the LHS and RHS dimensional formula. So force is m L raised to 1 T raised to minus 2 is equal to m into acceleration ka what it is, L T raised to minus 2. So if I combine and write it, it becomes mL T raised to minus 2. So if you see the dimensions on both the side, the dimension of LHS is equal to the dimension of RH. Yes, right? So this is how we write the dimension of the given physical quantity and the principle of homogeneity which we discussed. So except this also, we have many physical quantities like heat, temperature, specific heat. So that time here, not only MLT, we take one more dimension as theta. We take it as theta also. So just few examples we will discuss, then we can stop. Okay, so few examples like first one, I'll take temperature. That is temperature. So here temperature is measured in terms of what? Kelvin. Temperature is measured in terms of Kelvin. Its dimensional formula is written as it is a fundamental quantity. It is not depending on time. It is not depending on length. It is not depending on mass also. M raised to 0, L raised to 0, then T raised to 0. But here theta raised to 1 it becomes. This is for what? Temperature. Suppose if you take heat, the dimensional formula for heat, we write it as m L raised to 2 T raised to minus 2. M L raised to 2 T raised to minus 2 is for heat. Then next we write it for specific heat also. So for specific heat, how we write, that is, it is written as m raised to 0, L raised to 2, T raised to minus 2, theta raised to minus 1. This is for specific heat. So like this, we have for mechanical heat, then van der Waals constant A and van der Waals constant B, Planck's constant, then Wien's constant. So like this, we can take many physical quantities and the dimensional formula of that. So as you study higher classes, you will come across the other terms except MLT also. Okay. Here you see one, that is just a revision of because in this chapter what all we discussed, that is fundamental forces we discussed, the properties of the fundamental forces. Then what do you mean by physical quantity, types of physical quantity, unit, types of unit, how to identify and how to write the unit, then dimensions, then how to write the dimensional formula. So just at the end, we will just revise what all dimension formula means, extra examples we can see. So here one equation I'll take, that is F is equal to G m1 into m2 divided by r square. See here, force is having some dimensional formula, mass also is having this m1 m2, then r is also having some dimensional formula. I want the dimensional formula for G. Can we calculate the unit and dimensional formula for this G? We can write it as F r square divided by m1 into m2. So first I'll write the unit. The unit of force is Newton. and the unit of R is meter square divided by kg square is the unit. It can be written as Newton meter square per kg square is the unit of G, that is gravitational constant. How to write the dimensional formula now? So force is written as ml t raised to minus 2. Then R is written as L raised to 2 divided by mass. Again, this can be written as m raised to 2. So simplify this one. What it becomes? M. So this 2, if it goes to the numerator, it becomes minus 2. So plus 1 minus 2 is what? Minus 1. L raised to 3. T raised to minus 2. So not only for the given formula, we can calculate the dimensional formula for the universal constant also, like van der Waals constant, this gravitational constant, coefficient of viscosity. So like this, we can calculate the dimensional formula for constant values also. So this is how we can calculate the dimension formula for any given physical quantity. So here one question they will give, that is there any quantity or among the quantities which has no unit? So which one we can write? See here, that is strain is a quantity which has no unit here. Why? Because strain as well as a Poisson's ratio. So strain is what? It is the ratio of the change in dimension to the original dimension. So when we say change in dimension, suppose if the change in length is there divided by original length, the unit will be meter by meter. So meter by meter, what we do? We cancel both. Therefore, it has no unit. So they may ask you question like, among the given quantities which has no unit and no dimensional formula, that is strain. Strain is a quantity which has no unit and no dimensional formula. Name the quantity which has a unit but not dimensional formula. That is angle. Angles are having the unit but they don't have the dimensional formula here. So like this, we can write the dimensional formula for many quantities. Again, in the next class, we will continue the dimensional quantities for electricity and the terms related to electrostatic and electromagnetism. Okay, students. So let us continue other terms in the next class. Thank you.